Okay, let's start. This is the topic of electric current in charges. So we will start with charge because we think it is more basic quantity. But in physics, current is considered as basic quantity and charge is a quantity that depends on current. If somebody asks you to define charge, charge can be defined as charge equals to current multiplied by time, or it is product of current and time. So charge equals to current and time. Remember, the current must be measured in amperes. Time is always taken in seconds. So unit for current is taken in amperes, time is taken in seconds, and charge will have a unit ampere second. Ampere second. 1 ampere second is also known as 1 coulomb. 1 coulomb of charge passes a point if a current of 1 ampere is set for 1 second through the point. If 1 ampere constant current is flowing through a certain point for 1 second, a total of 1 coulomb of charge has passed through. Charge is a quantum quantity. It is a quantity that depends on discrete numbers, and the total charge is always multiple of number of charged particles and charge on each particle. So if you want to find out the total charge will always be a multiple of a whole number multiple of a fixed number. That number is known as elementary charge. So here's the relationship. Total charge equals to number of charge carriers multiplied by charge on each carrier. The charge on each carrier here will be elementary charge. Elementary charge means charge on electron or charge on proton. The value for elementary charge is 1.6 into 10 to the power minus 19. Charge on electron is minus E, means minus 1.6 into 10 to the power minus 19. Charge on a proton is plus E, means plus 1.6 into 10 to the power minus 19 coulomb. No matter how large or how small the charge is, it is always a multiple of 1.6 to 10 to the power minus 19 coulomb, at least for your IGCSE. Okay. So here's a question. Calculate number of protons that can make a charge of 1 coulomb. How many protons can make a total charge of 1 coulomb? So remember, each proton has a charge 1.6 into 10 to the power minus 19 coulomb. And we have to make a total of 1 coulomb. How can we find out number of charged particles? Any ideas? Now, in order to calculate that, the data we have is total charge is 1 coulomb, elementary charge is 1.6 into 10 to the power minus 19 coulombs, and number is what we need to find out. So deranging formula, N equals to Q over E, N equals to Q equals to 1, E equals to 1.6 into 10 to the power minus 19. Final answer should be 6.25 into 10 to the power 18 protons. If we have them together, we have a total of 1 coulomb of charge. Now, another question. A charge of 4.5 millicoulombs, milli stands for 10 to the power minus 3 or divided by 1000. So 4.5 millicoulomb pass a point on a circuit in 20 minutes. Calculate current in the circuit and charge that passes the same point in 1 hour. So here we go. Do you think you can give this question a try, or should I solve it? Okay, me doing it now.
That's after.
You have to what?
I have to go.
Okay. Okay.
No problems.
4.5 into 10 to the power minus 3 coulomb. And this is charge. And time equals to 2 minutes. That means 120 seconds. So current, which is charge divided by time, should be 4.5 into 10 to the power minus 3 divided by 120, and just used a calculator, and I know it is 0.1234576. So 3.75 into 10 to the power minus 5 ampere. Okay, if the current is supplied at the same rate, how much charge will flow through the same point in 1 hour? Again, you use the same formula, charge equals to current multiplied by time. Use the same formula. That is one thing. You need to know the formula. Secondly, you need to know that time must go in seconds. So hours must be converted into seconds. Let's see if you can solve this one. So to find out total charge pass through, we multiply current with time, but remember time must go in seconds. So 3.75 into 10 power minus 5 into 16 to 60. This is for the time, and we should get 0.135 coulombs. Now, how many electrons will pass the point in 1 day? Again, it is the same kind of question, or all everything is same as we have done in the previous question. I'm talking about the one that is on the top of the screen, where we calculated number of protons for 1 coulomb. Now we need to know how many charged particles. In this case, the charged particles are electron. They pass the point in 1 day. Actually, time is given in the form of day. We first have to convert it into seconds. And then that will give us the amount of current and time. They multiplied, they give us amount of charge, and we can use formula charge equals to Ne to find N. We already know value of E. So give this another try. See if you can find out how many electrons they pass the point in 1 day if there is a constant current there. There. Let's see. Now, it is 2.03 into 10 to the power 19 electrons. So, see, this is the calculation. This is current multiplied by, this is time, current multiplied by time divided by elementary charge gives us number of electrons. Okay. Other method is first you calculate charge. Okay, you calculate the answer for this one, and then put that answer over here and get this answer out. So who got this answer right? Who got 2.03 into 10 to the power 19? Repeat that. There are two kinds of forces in physics in general. One is a force that requires a physical contact for its execution, and one force is that does not require any physical contact. For example, friction is when two surfaces are in contact with one another and trying to slide on one another, and friction cannot exist without a physical contact. Similarly, tension is a kind of force that can be applied with a physical contact. Okay. Normal contact force, which has word contact in it, also depends on also a kind of contact force because it requires a physical contact. Now let's think of forces that do not require physical contact. For example, gravity. Gravitational force does not require any physical contact. Electric force, positive charges repel other positive charges, or negative charges repel negative charges, or positive charges attract negative charges, or negative charges attract positive charges, and they can do that from a distance. They can exert force on one another without a physical contact. So such a force is called a field force. Gravity, electric force, magnetic force. The list is not very long in this case. There are not too many field forces. Okay. Electric force, magnetic force, gravitational force. They all do not require physical contact. I hope you are old enough to do that to your younger siblings, that you put one piece of magnet on the top of the table and the other piece of magnet on the bottom side, and by moving the bottom magnet, you can deceive your siblings, younger siblings, that there's some kind of magic happening which is making the magnet move. Okay. Either you have done it to your younger siblings or your elder siblings have done that to you. So a magnet which is on the top of the table is affected by another magnet which is on the bottom side of the table, and they attract or repel one another. So such forces that do not require a physical contact are called field forces. Electric field or electric force is also one of the examples, and the electric field or any field in physics is a three-dimensional region. Electric field means three-dimensional region, three-dimensional space around a charge. The other charge can experience a force. Electric field is a three-dimensional region around a charge where other charges can experience a force. Now, electric field is a vector quantity. A vector quantity means a quantity that has direction. What is the direction of electric field? There are only two types of charges, positive and negative. So rule is that like charges will repel one another, and unlike charges will attract one another. So positive will attract negative, and positive will repel one another, negative will repel one another. Like charges will repel, unlike charges will attract. Now, direction of electric field. To investigate direction of electric field, what we do is we just place a positive test charge where we want to investigate a field, and direction of force that charge experiences because of that electric field is the direction of electric field. So whatever the direction, a positive charge experiences a force is the direction of electric field. So here's a grammatical explanation. If this is a positive charge, this is the direction of force, then this will be the direction of electric field. But if it would be a negative charge, then this will be force experienced. Then this will be the direction of electric field. So direction of electric field is always opposite to the direction of force. Direction of electric field is always opposite to the direction of force on a negative charge, and it is always along the direction of force on a positive charge. So in any electric field, if there is a force experience by the positive charge is in any certain direction, that will be considered as direction of that electric field. So there's a definition, because examiner never gets tired of asking this question. This is a very favorite question of examiner. What is the direction of electric field? Or define, how do we define direction of electric field? Direction of electric field is defined as direction of force experienced by positive test charge in the electric field. On the basis of that, we can make all these electric fields. Listen, let me draw this again for you. So this is a positive charge. Okay, and this dot, I hope you can see that small dot on the top of the screen. This is a test charge. So you should know the test charge is always positive. The bottom positive charge is a fixed charge. This is a small test charge. What will be the direction of force on the test charge because of the main charge? Do you think the main charge will attract the test charge? Will it repel the test charge? Will it make it go towards right? Or will it make it go towards left? What will be the direction of force because of the positive charge on the test charge? Will it be A, B, C, or D?
A, sir.
Good. So in this point, force will be along A because the main positive charge is supposed to repel this charge. So if I bring a positive charge on the top, it will experience force in this direction. So it means on the top of this charge particle, there will be an upward field. Let's say if I bring the positive charge here, what will be the direction of force now? So if I bring it here, the force will be downwards. On the left, the force will be I hope now you understand that why we say that the positive has an outward field, because if we bring a positive charge close, it will be exerting an outward force on that positive charge. So this is how the electric field should look like. Similarly, if I have a negative charge and I bring a positive charge to investigate the direction of electric field, so whenever I have a positive charge, the main negative charge will attract it towards itself. That's why when I draw the electric field of a negative charge, it is always pointing inwards, because it exerts an inward force on positive charge. A positive charge, on the other hand, exerts an outward force on a positive charge. That's why positive field is outward and negative field is inward. Okay, tomorrow resume from the same point, and we will discuss what will happen if we bring a positive charge close to a positive charge and negative charge close to a negative charge, how the electric field between the plates should look like, and we will also start and complete actually electrostatic induction. Okay, tomorrow we'll have class on the same time. See you tomorrow.
Allah Hafiz.
Yes.